All right, good afternoon. So we're going to be here for Calc 2, and we are talking about putting it all together and trying to figure out which integration technique to use, and maybe some integrals that haven't been covered yet, and just some of the weird stuff. Okay, not too weird, but a little bit. If you are interested in learning, doing more, watching people do some crazy integrals, Black Pen, Red Pen is just an awesome YouTube channel for watching integration or watching techniques of integration. That guy is really amazing. So I encourage you to find out his channel and to watch those. And I would warn you, don't come the next day and say, hey, could you do this one too? Probably not. Okay, that guy's really good. All right. Let's go ahead and start taking a look at some of these. So this is integral t over t to the fourth plus 2. Okay, we're going to see if we can. It's indefinite, so we're going to need a c. Okay, so here we go. We've got t over t to the fourth plus 2 dt. Okay, and okay, so let me just take you through my thought process when I'm looking at this. I'm seeing something that has like a power of 2 to it, plus a constant down in the bottom here. So that's reminding me of this form, right? T squared plus 1. Okay, integrating that. And I know that this one is inverse tangent. Okay, it would be inverse tangent of t plus c. All right, but it's not, it doesn't quite match up because I've got something going on here. You see, if I let u just equal 4t, or t to the fourth rather, then my du is going to be 4t cubed. I don't have one of those, okay? Nothing really makes sense to kind of separate out. So I'm kind of liking this tangent idea, but instead of t squared, I'm going to say, or instead of just t here, we're going to say, well, how about we let u equal t squared, and then my du is going to be 2t dt. Now I've got a t here, right? We've got a matching t. I'm a lot happier about this, and I'm thinking, well, maybe I am on the right track. Okay, so what we're going to do is we're going to do a 1/2 integral of 2, because that's 1, right? 1/2 times 2 is 1. Then we have our t and dt, and then we have, right, this is now u squared plus 2, and then we have a du, and our there's our dt rather. So this piece here, right, this is this guy right here, 2t dt. That was my du, all right? So let's see what we have. We have 1/2 integral of du over u squared plus 2, and that's pretty good, right? We are almost looking at this form right here. Okay, but I've got a 2 sitting here. Okay, I need it to be a 1. So what I'm going to do is I'm going to pull out another 1/2 here. I'm going to say, well, this is 1/2 times, and then I've got a du over, okay. Now, this has to be a 1. What did I do to make that a 1? I divided it by 2, right? Or I multiplied by 1/2. So we're going to put another 1/2 in here, but I just can't go around just multiplying this one by 2, right? This has got to be a, right, this has got to be a u squared over 2 plus 1. Okay, so we're almost there. All right. So one more substitution, and there's this, for me, this is a pretty common technique in this particular chapter, is we have to do a u substitution and then like a w substitution. So what I'm going to do is I'm going to say, well, what about this? We have du over, and then instead of u squared over 2, I'm going to say this is u over the square root of 2 squared plus 1 integral. We've got that 1/4 out in front here. Okay, so do you see what happened with this, where I could do that? Now we're about set. Okay, and if you haven't done a couple of these in a while, I encourage you to do it my way because it makes it real obvious. But you know, if you memorized the more advanced version, that's fine. So we're going to go ahead and I'm going to say let w equal u over the square root of 2. dw, right, equals 1 over the square root of 2 du. And then we can go ahead and say, well, this is the square root of 2 dw is equal to du. So my 1 du gets, if I want to replace it with w, I've got to scale it by the square root of 2 in order to do that. So we're not like multiplying by 1. I'm just saying, well, du is equal to this scaling factor, right? Kind of like 1 inch is equal to 2.54 centimeters. I don't have to multiply and then divide by 2.5 centimeters. We're just going to multiply this thing by 2.45 to get the inches. So let's go ahead and do that. So we've got du is equal to square root of 2 dw, and then at the bottom here we're going to have w squared plus 1. Let me just push this outside. Square root of 2 over 4 dw over w squared plus 1. This is exactly what we want, okay, in order to deal with this. So this is going to go ahead and be, this is the format we want because this is our inverse tangent. Okay, so we're going to have the square root of 2 over 4, and then we have tangent inverse of w plus c. And now we've got to untangle this knot we made that is w, right? And w was equal to u over the square root of 2. So it's square root of 2 over 4 tangent inverse, and then here we have a, u over the square root of 2 plus c. And then what that was u, and u was equal to t squared. Okay, so we have integral of 2 over 4 tangent inverse of t squared over the square root of 2. Okay, plus c, and that's how we're putting that together. All right, so I'm trying to avoid the fancier types of integration techniques, okay, because they're they make things way more complicated. But I'm keeping them in mind that I might have them. But let me try the basic ones first, right? Let me try direct. Direct wasn't going to work, and then let me try u substitution. And I might have to do u substitution a couple of times, but doing u substitution twice versus doing integration by parts twice, I'd rather do u substitution twice. So it's a little convoluted, but at the same time, it's not so bad. Okay, it's not as bad as having to do some of the fancier things twice. All right. So let's see here. All right, let's try another one here. Let's say, okay, how about this one? This is integral of, we have 15 ln x, okay, and it's divided by x square root of 5 plus ln x squared dx. Let me write that so it looks like it's actually, with letters. So we have 15 ln x root 5 plus ln x squared dx. That looks a little better, not much, but a little bit. Okay. So with this one, okay, I like the fact that there's an x down here. Okay, that's kind of screaming to me that the correct substitution is going to be let u equal ln x, and then my du is going to be 1 over x dx, because right here is my 1 over x dx is this business right here, right? It's that. Okay, there's my 1 over x dx. Okay, so let's go ahead and make that happen. All right, let's go ahead and see what's going on there. So we have integral 15 remember natural log was now u, okay? And then we have the square root of 5 plus u squared, and then we have our du, because that's my dx over my dx over x, all right? And this is looking pretty good. Okay, I'm pretty comfortable with this. We could say, you know, 5 plus u squared. We could say, again, we can do another substitution. So how about we try let w, okay, equals, I swear to you, about this point in the class, point in Calc 2 when I was doing it, I was so tired of writing u substitutions. All right. So I ended up doing let mushroom equal, and then we'd have d mushroom. We'd have, you know, happy face equals, and then d happy face. I mean, just start using different symbols if it keeps things more entertaining for you. But you know, I get the monotony of u substitution after u substitution after u substitution. So you know, you could do a theta, right? So pick a letter you need some practice with your penmanship, and use that. Okay. So here we go. We're going to say we have 15 integral, and here's my 2u divided by 2, right? And then du. Oops, I don't want that. I want, oh yeah, we're still there. We're still at du. We're good. Okay, and then I've got over w, the square root of w, right? So here's my dw, is 2u du, right? So this is 15 halves. I've got integral w to the negative 1/2 dw, because that's my 2u du, right? And then now this is a, you know, this is a normal, this is an integral you learned in Calc 1, right? So we're just going to add 1. So we're going to get 15 over 2. We have w, right, to the 1/2 over 1/2, okay, plus c, right? So this is really going to be 15 over 2 times that, okay, and then we have a w to the 1/2 power, okay. What was w? W was 5 plus u squared. All right, what the heck was u? Well, we're going to go back up to u. U was the natural log of x. And there's our answer for this thing. Okay, so that's again, it was the same technique, right? I'm sorry about that. It was the same technique. We did a u substitution. We found that it didn't quite go far enough. So once we got to the end, we said, okay, well, let's try another u substitution and make sure we can get everything kind of sorted out here. Okay, so that's what we do. All right. So let's see here. What else do I want to do with you guys? All right. Well, here's one. Yeah, we can. Oh, that was okay. Let's keep that too. All right. So this also has a couple of just nice integrals in it, using some of the previous chapter stuff, or using some of the early chapter stuff. So we have an integral of 9 sine cubed x over cosine x, right, dx. And there's not just one way to do a lot of these, okay? So just because you didn't do it exactly the way I did it, like that's fine, okay? That is fine. But I notice I have a sine, a powers of sine, I have a cosine here. I'd really like to let my u equal to cosines because, you know, it's on the bottom. If I let u equal sine, then I've got a du on the bottom, and then it's going to work, right? If I try, I mean, you think it's like, well, that's going to work, right? We have u cubed, but then I've got this, right? Then I've got that, and this dx is not gonna do so well for me. Okay, so I'm gonna end up with like a du on the bottom. Can't do that. It's not an integral. Okay, du's got to be on the baseline. If you find your du inside of a radical or up in an exponent or something like that, you've guessed wrong. Okay, so this would be the wrong guess. Fortunately, we remember that sine squared plus cosine squared is equal to 1. Okay, so we should be able to pull something out of this where we could say, well, this is 9, and this is, right, sine squared, right, is 1 minus cosine squared. Sine squared x is equal to 1 minus cosine squared. And this, we can bring this out. We can say, well, this is sine squared x times sine x dx all over cosine x. All right. So this is going to be 9 in a row. Okay. And then we have a 1 minus cosine squared x all over cosine x. Sine x dx. All right. Let's try this out and see what happens. Okay. Let's just try this out and see what happens. So we've got let u is equal to cosine x. Okay. Du is equal to negative sine x. Okay, so I'm going to need to add in, right, a negative sign here, right? So we're multiplying by 1. Okay, here's my du now. All right, and then we can go with this. So we're going to have negative 9 integral. We have 1 minus u squared all over u. Okay, times du. All right. Now, the nice thing about fractions like this is you can separate them, right? Because it's on the bottom versus the top. So this is negative 9. I've got a 1 over u. Right? We've got a 1 over u minus a u squared over u. So just minus u du. All right. So let's go ahead and check this out. So we have a negative 9. Integral of 1 over u, that was natural log absolute value of u, and then minus 1/2 u squared. So that's a pretty standard. See, this one I didn't even need to do several integrals, right? There's several substitutions. This is just going to be absolute value of cosine x, natural log of it, minus 1/2 cosine squared x plus c. I think this is times like that. Okay, so there's our integral. Okay, so maybe negative 9 natural log cosine x plus 9/2 cosine squared x. Okay, we can do that. Let's see. Okay, so that's another, you know, that's revisiting my trigonometric integrals. So we're going back and looking at that. Okay. Let's see, what else do we want to do with this here? Oh, this is a good one. Okay, I like this. This is definitely one we need to see. So this is integral. Okay, and it's always integral. E to the, oh no, just dx. And then 32 plus e to the x here. Okay. So when you see this, right, we've got a 1 plus some constant plus an e to the x here, dx, and we want to, you can put a constant up here, leave it as a 1, because the first thing we're going to do is we're going to push this over here. But this is a very famous integral, and you'll see this quite a lot. Okay, so what we're going to do here, again, there's a couple of different ways to go. The way that I think is the best, or the way I like to do this, is we're going to multiply top and bottom here by e to the negative x. Okay. Like, why would you do a crazy thing like that? Well, here's what's going to happen. Okay, we have 32 integral. Okay, e to the negative x on the top here. And on the bottom, right, we've got our 32 e to the negative x plus 1. So what this does for us is it puts the e to the negative x up on the numerator so that when I say let u equal whatever's in the denominator, because this is a problem, okay, 32 e to the negative x plus 1. Okay, du, right, is just going to be negative 32 negative x dx. Okay, so at that point, I want to put this back in, right? So this is going to be, again, you have negatives. You always have to watch your signs when you're doing all of this stuff, both your SINEs and your GNs. So we have negative integral negative 32. Okay, we didn't really need to do all of that red. So we have a negative integral negative. That looks terrible. What am I doing? All right. So here are the two negative signs I put in. Okay. 32 e to the negative x dx. And on the bottom, we've got 32 e to the negative x plus 1. And let's go ahead and substitute now. So we have negative integral negative 32 e to the negative x. Well, that was my du. That was the whole point. Okay, and then we have u on the bottom. All right. And this is a nice integral. Don't think that everything that has a fraction happens to be a natural log. Okay. The first one, it was inverse tangent. Right. The second one, or the one we're doing now, that's a 1 over u du kind of a situation. Okay, so that's negative ln of u plus c. And now it's time to push everything back in. So we're going to say, what the heck was u? U was 32 e to the negative x plus 1. So this is negative. And then, oh, wait a minute. What was this? It was 32 e to the negative x plus 1. Right. Now, you might be tempted to put the negative in here, and that's actually not so bad. Actually, I don't need the absolute values because this is always positive, and then we're adding 1 to it. So this is always positive. But it's not going to be, you know, don't put the negative here and here, okay, and swap that. It's over the whole thing. So it's a little bit different, okay. So here we go. We have negative ln, and then just 32 e to the negative x plus 1, right, plus c. All right, that's a very common integral, though. You'll see this again and again. Okay, you'll see this in differential equations, I promise you. And how do you do this thing? I mean, there are other techniques, but I think the easiest one, right, is to multiply top and bottom by e to the negative x. Let's see. Can I think of another way to do this? At the beginning, we could have said, right, we still have this guy. So we have 32 dx, and then this was 32 plus e to the x. That was what we had. Yeah. Let's see. We could set u equal to 32 plus e to the x, yeah? And du is equal to e to the x. But e to the x is equal to u minus 32. Okay. Putting that over there. Yeah. And then we can start substituting other things. Okay. So let's see here. du is that dx. All right. Yeah, this one gets a little tricky to do this one here. Let's see here. We had we're going to have 32 plus u minus 32. And what are we going to do with that one? Du is just that dx, so we have dx over e to the u. Okay, so we have 32. This is du over e to the x over u. E to the x was equal to, yeah, so here we go. So this is going to be 32 u minus 32 du. We change the e to the x into this thing and integrate that. And at that point, we get to do partial fractions, and you can see how much fun this is going to be. So, yeah, this is good. It still works. It's correct. But you'll see already, like, how many steps did we end up with versus doing this. And I think this is just a better way to go. Okay. So that's not so bad. So let me see here. That might be what I want to do with this today. Oh, there's one more. Okay, there is one more. So shorter lecture today though, but we're still gonna. Where did you go? I did not want to do that one right now. Come back here. Where are you? Yes, I write these out beforehand. I already know. If I don't do that this time, then there's a lot of places to get lost. So yeah, forgive me on this one, but I wanted to keep things kind of like not getting everybody lost with where I was going with some things. All right, what are we doing here? I don't know what that is. I don't know how I did that. I don't want to know. Where are you? What did I do with you? All right. Oh, there we are. Okay, there we are. All right, so let's have a look at this. All right. So we have the integral of 4, and then we have 1 plus the square root of x to the 7th dx. All right. Now, again, this is going to be when we're going to have to twist the u substitution around a couple of different ways. Yeah. So we're going to go ahead and say let u is equal to 1 plus root x. Okay, because this is kind of a pain. All right. But then we're going to say let root x equals, right, u minus 1. And then we're going to square both sides and say x is equal to u minus 1 squared. Okay. The reason why I want to solve for x is because I want my dx, all right, I know this seems kind of crazy, is to do that. All right. So now I've got my dx in terms of my u's. So we've got integral 4. I've got a u to the 7th power here, right? That's this guy right here. This is u to the 7th. And then my dx is equal to 2 u minus 1 du. Okay. So yeah, we can go ahead and solve this now. I know it looks kind of crazy to do this, but we are allowed. So this is 8 integral, and we have u to the 8th minus, right, u to the 7th. Okay. This is all times in here, so 2 times 4, okay? And then this is all du, all right? And it's nice because this goes back to being like a polynomial. We can integrate these very easily. So this is 8, and then we have u to the 9th over 9 minus u to the 8th over 8th plus c. You say, okay, well, what the heck? Great. What the heck was u? Right, this is all 8 times all of this stuff. So we have 8/9. Okay. U was 1 plus root x. Raised to the 9th power. Okay. Minus 8 over 8. And we have u to the 8th. So this is 1 plus root x to the 8th plus c. All right. So, yeah. Every time, every one of these, I started off with the u substitution first and checked to see how far I could take that before I'm going to start venturing into like weird triangle integrations or, you know, trig substitution. We did one trig substitution, we kind of had to. Okay, or integration by parts, because those are all more complicated techniques, and we really do. We want to exhaust some of the easier stuff first before venturing off into some of the difficult things. Now, there's still like x times exponent. You know, unless we have a very convenient u and a du, you're stuck using a integration by parts. Okay. If you want to have some kind of a polynomial times a logarithm, we're integration by parts. You have inverse trig function, almost always. Okay, integration by parts. Although not always, right? Not always, because you have an inverse trig function. If that was u, and your du is somewhere in the derivative, right? If we had an inverse tangent x here, and we had an x squared plus 1, well, now, you know, letting u equal tangent inverse of x is fine, because my du is 1 over x squared plus 1. So we have that. We could let this be u, and then we'd have our du. So again, you always want to try the u substitution first and see if you can make it work. And if you can, great. But if you have to, like, if this peters out, and we're like, well, that was a dead end. I'm like, that's okay. You have, you know, 2 other techniques, right? You have integration by parts, very powerful. And then if you've got something with a square root in it, especially on the denominator, then you might be able to use some sort of substitution like x is equal to, or sorry, theta is equal to sine x, right? Or no, x is equal to sine theta. What am I doing? Sine theta, or x is equal to secant theta, depending on the kind of triangle you have. Okay, so, or maybe tangent. Yeah. Okay, maybe tangent theta. Okay, and then pursuing it from there. All right. So this, if you have square roots, you want to do something like this, but only after you've explored the substitution thoughts. Okay. So I'm going to go ahead and stop there, and we'll do a couple more of these tomorrow. Actually, tomorrow is numeric integration, and the week after that, we're going to go back and review everything in chapter 7. Okay. You're going to want numeric integration because, quite frankly, we don't, most of the stuff that you integrate in real life, you know, it's by spreadsheet. We don't have functions. We don't have closed form functions to do things. We've got, you know, a bunch of points, and then you have to integrate those. Okay. So I'm going to stop us there. I will see you tomorrow. Have a good day, and good luck.